So, the main thing to realize about the submarine problem is the minute you introduce 3 dimensions, your trigonometry is not going to be as easy as it was before, because now to break down, basically, let me see what's going on here. This is the problem where 30 degrees above the horizontal with a heading to the northeast. So you have several things going on here. So let's say this is north. Yeah, let's do that. Let's say this is north, this is south, west, east. This is up, this is down. Okay. So it's going to the northeast at an angle of 30 degrees above that. So it's okay, cool. Northeast, what does that by itself mean? It's true about it in this plane, the XY plane. It's going to be 45 degrees here, right? Let me draw this like this here. So this is kind of like what's called, just to get a little ahead of myself, this is the projection of its motion in the XY plane, or directional plane, whatever the hell you want to call that plane. Once I call it northeast, west, south. We guys doing so far so good? Northeast means exactly northeast, 45 degrees away from either one. What it's really doing, though, is it's going kind of in that direction, but at the same time it's going up 30 degrees from there, right? Okay. So where you guys go? This is not my favorite problem in the world. So 30 degrees up from there is where it's really moving. So it's going to the northeast up 30 degrees. Right, because it's got all 3 dimensions to play with. So the problem, you got to realize it's a 2-step problem. You got to break it down twice to really get this, because the question says what is its components in all the different directions, right? The first main realization, what's the first angle you use to break this thing down?
45.
Yeah, actually it doesn't matter, but to me it's easier to break it down using the 30 degrees first. If I can throw this thing into this plane, and how do I do that? By removing the up component, right? If I can remove the up component, where's it moving? This way in this plane, and then 45 degrees is sitting there waiting for me. So I'll do the first step. Or maybe I'll get you guys to help me with the first step. What is this component here? So and it tells me, what's it tell me? It tells me 20 knots. Sorry. So it's going at 20 knots. Yeah, so this would be 20. Is it sine 30 or cosine 30? Sine 30. Cool. So that's one piece done. There's a gimme. Now when you put the other piece, 20 cosine 30, where is that? Where is that? Do I already have it drawn up here? Yes, I do. It's the purple dotted line. So this here would be 20 cosine 30 degrees. What do you have to do with this then? It's basically almost done then. Let's see. That is the speed in what direction? And they want the speed up and north and east. So what do you have to do with this speed? You have to break it down into its parts. So you have to treat this, it's a number, isn't it?
Yeah.
So then you have to do trig to this thing, put a sine and a cosine after it. And just make sure you get the right direction. And it's 45 degrees, so you can't go wrong.
How is it cosine?
Let me see if I can, of course, you know, 3D is always, oh, last time I had only black to work with, now I have, oh, now I still don't have black. So, if you look at this triangle here, that triangle, see that? So let me draw it again here. So this is the thing that's at 45 degrees, right? This is the dotted purple. Cool. This angle here is what? 30. And this is the 20 knots. So straight up and down, straight up and down would of course be 20 sine 30 because sine goes like y. And this piece would be 20 cosine 30, right? But then that piece, the thing about this problem that makes it hard, which actually in the end, it ain't that hard at all. That is a speed, but it's also got parts to it, so you got to break it down into its parts. The funny thing is, I'm going to come back to this a couple chapters from now and say, hey, the stuff we're doing right now, it totally relates to the answer you got here. Oh, neato. So keep this one banked. It's going to become, this is a nice physical interpretation for something mathematical we're going to do later. All right, I got it on video. Okay, may I? How you guys doing? This is a great way to spend your Monday afternoon. So do you see that's, if you hadn't looked at that problem yet, obviously that's a very difficult one to do totally on your own, because you probably have not done something exactly like that.
I thought it was
Depending on your pre-calc teacher, how evil they were.
For some reason I thought it was two-dimensional and I just did that.
Ah, I got you.
So easy, I was like, oh, that.
Yeah, you got to have that extra, that plane that's just north, south, east, west, but then a whole other axis that's up and down. That makes it belong at that number in this problem set. Yeah.
Going back to problem 62, those vectors Q, R, S, and T. Did you say those are all coplanar? These are all the same vector?
Let me see. Let me look at it. Yeah. They not the vectors are coplanar. So that might have been the terminology, but the question that somebody asked, I kind of knew what they meant. Their points that they point to are coplanar. And that makes their angles the same, which makes a lot of the other way to do this unnecessary. Because the angles are all the same, so it's...
And their lengths are the same, is that what you said?
Their lengths are definitely the same, because they're all the same distance away. And so that's why this problem is put here, because there really isn't that... It looks really difficult. It's number 62, but it isn't that bad.
It doesn't mention what the angle was under, or we just find it from the vector?
You could. There's a way to do this where you figure out the angle if you really wanted to.
But you don't need to.
You don't need to. You do not need to. The beautiful thing about vectors is that they inherently have an angle to them. It's a part of the vector. Just by me writing this, I've written how long it is, and I've written what angle it's at. I can't see it, but a lot of the math we learn deals with it directly. I don't have to tease them out and put them together and put it, no, it just attacks it directly. Okay. If I had to break this up, then why the hell would we even talk about vectors? What good would they be? If I had to break it back down into its parts, screw vectors. But thankfully, there's a reason that we have them. It has a lot of information packed into one little thing. Okay. Any other questions from? Yeah.
Is there a convention as to how to use node and south? Because I happen to think the X supposed to be node.
Yeah, I was thinking about that as I was writing this, but there's really no convention. As long as you show me what you're doing. The reason I did this is because it makes more sense when you look down at it, right? If I were to draw this, and actually I was thinking backwards then because this would be the X and the Y, but I really just wanted to draw it to make it easy on me to draw it. And as long as you show me what you're considering to be north, south, in fact, very often you'll see this is north. If anybody does any boats, you often assign this to be north and east, talk about your bearing based off of that. North is this way. So it is very arbitrary as far as they have to relate the same way, of course. You can't say, well, that's north and that's south. But as long as you show me how you're setting it up, you're good. And those are, again, I'm going to say this a lot, so hopefully this doesn't get old. Those of you who had physics realize you can call one way negative and the other way positive or the other way. It doesn't matter. As long as you're consistent, it doesn't matter. Cool. My answers will be the same here if you compare to somebody who turned them around. Okay. Any other questions from the homework? Okay. Okay. So, just to kind of go back for a second. I think the last thing we did last time was we did the quick quiz from section 11-2. clear, is that no matter how many dimensions this is, and this, no matter how many dimensions it is, a lot of what we learned in section 11.1, which only dealt with 2 dimensions, applies. Right? If I want to get u plus v, that would be u1 plus v1. I think I can go ahead and write that there. You just keep doing the same thing. u2 plus v2, u3 plus v3. That's how you add those vectors. Physically, can you imagine what a 12th dimensional vector would look like? No, screw it. In fact, I hope you guys understand, a lot of times there's no physical necessity to graph it because they don't define physical dimensions. They define the temperature and the time and the density of the water in the air or whatever. I'm thinking about taking a reading outside the door. Yeah?
How do you draw it going past 3 dimensions?
That's what I'm trying to say. Most of the time, they don't relate to physical dimensions. So most of the time, the math itself is enough. Trying to come up with a way to graph it is unnecessary and confusing. If you are talking about physical dimensions beyond 3, and I'm not talking about time as a 4th dimension, I'm talking about physical dimensions, then you are in a very advanced physics class, and we don't need to worry about that here, because we're not in a very advanced physics class. The most we're going to do, of course, is 3. I don't know if you guys have ever heard of a hypercube. Anybody ever heard of a hypercube? It's not a cube that's... You can't... Calm down. It's the best attempt somebody's made at trying to represent a 4-dimensional figure is, if you look it up, hypercube. That's something for you guys to look up when you go. You see it a lot when people try to describe the 4th dimension. And I don't mean time here, I mean an actual physical 4th dimension. Cool. But you're not obviously going to have to do that. It's hard enough to do 3. 4 is basically impossible for a human. Right? Okay. U minus v, much the same way. What about the magnitude of u? What would that be?
The square root of all of those components squared.
Yeah, exactly. U1, U2, blah, blah, blah. So, okay. So, the beautiful thing about vectors is so much of the math for the vectors is the same no matter if you're in 2, 3, 4, 5 dimensions. You guys with me? Now, when I say that, notice I didn't say all of the math is the same. I said so much of it is the same. What gets really difficult sometimes is knowing when certain math doesn't work and certain higher. Most of the time there's something that works in 2 dimensions that doesn't work in any other dimension. There is something that works in 3 that doesn't work in any other dimension. I'll be very specific when we hit those. You guys with me? So I mean, vector, scalar multiplication is the same here. All that stuff is in here. Okay. Good, good, good. How are we doing so far? Maybe. Okay. So, I mean, if I give you a problem like this, and I say, what's this? And you moan, I will throw you out of my class, because that is easy, right? If I said graph this, you should moan. And I'll throw myself out the class. Because that is basically impossible for us to do. But adding it is easy. If I said, okay, what's 3u minus 4v? Still, easy shit, right? That's easy. It's not required that you understand at all what this thing looks like. Because we've passed the ability for us to think about what this looks like, right? I can't think about what that looks like. I can't. Why? Because my brain exists in freaking 3 dimensions as far as I am aware of. So I can't think beyond that. So it's fine. Let go of that. We can do a lot of math with this. This has physical meaning. Cool? Because this could be, like I just said, this could be, obviously this is not temperature here, but this could be temperatures and humidities and whatever. And that one thing describes a certain time of day and a certain location. And then this could be the next location, like this could be the location here. And then, you know, so that's just another way to represent a bunch of variables. They don't necessarily represent graphable things. Okay, maybe. No, I don't want to bring too much of that in. There's a lot of physics you could not do without thinking about mathematics of n dimensions. And I'll leave it there. Okay, I don't think there's anything else majorly interesting here. No. Nothing. So let me give you one problem to try out. Actually, let's go ahead and do this. These vectors that you stated. Go ahead and do this. This should be quick. And do this here. And then I want a unit vector in direction of u with the length of v. Where you get that? The fourth one is the hardest one. I want a unit vector, no, not a unit vector, but a vector. I'm trying to give you a little clue as to how to do this. A vector in the direction of u that has the length of v. And your problem just like that, although in 2 dimensions, but it's the same math. And the answer number 4 is not going to be pretty. So don't freak out if you don't get a pretty answer. Unit vector, how do you create? I had unit vector up there earlier because I was thinking about the first step. The first step to number 4, I've given it away already, is you need a unit vector that represents the direction. So what direction do you want your answer to number 4 to go in?
U.
Direction of u. So you need a unit vector in the direction of u, because then it would have length 1. And if you wanted to have the length of v, multiply it by the length of v. Yeah. So how do you create the unit vector in the direction of u?
Divide by 90.
11. Exactly. Cool. So step 1 here is u over u. And step 2 is magnitude of v times that. here still need to take linear, like you're going to take linear algebra at some point, you'll appreciate just about everything we're doing the first few weeks in here will help you with a lot of that class. Neat. It's alright. Trying to do the math.
Report, can we just leave it right now?
Say again?
Report, can we just leave it like right now? I don't want us to do all the multiplication on that. And that like this.
Just leave it as a ratio of radicals in front of a vector. You can do that.
Okay.
Or you can bring that in. It doesn't really matter which way. Did I get all that right? Sorry.
Yeah.
Okay, thank God. Let's make sure my brain's working. The length of v, how do you get that? The square root of 9 plus 1 plus 16 plus 4. Is that cool? Everybody get that? So that'll be square root of 30, which you can't really simplify. So now I know how long the answer to number 4 has to be. It's got to be root 30. I just need its direction pointed out to me without a length associated, just so I'm pointing in the right direction. So I got to first figure out how long u is, and then divide u by it, and that'll be pointing me in the right direction. So if I do this, what will be 1, 2, 6, 22, 47?
Yeah.
So now this will be, let's just jump to this. I want it to be this long, square root of 30. I got to divide by its length, square root of 47. And I want it to be, so the u direction, oops, 1, 2, negative 1, 4, negative 5. And then there's really nothing you can do with this. And rationalizing it, no, screw that. It doesn't really help you anything. This is fine. Right? Okay. Did everybody get that? Why is it not good enough just to take root 47 times u? Why is that not good enough?
Because that's the same thing as our
You don't know what.
I don't know what length u is, so more than likely it's not a unit vector. So root 47 times u, will it have the length of v? No, it'll be longer. Right? If u is too long, this will be 2 root 47 long. It's too long. There's a lot of different versions of the word 2 in that sentence. Alright, how does everybody feel with that? So that should, it's new, but the mathematics is stupid easy. Right? And what dimension were we playing in? Who knows? The 5th dimension. So I don't want to hear any complaints about that kind of problem in the 3rd or the 2nd, because we just did the freaking 5th. And it'd be easy as hell to do the 80th, it would just be long, but it'd be easy. Okay. So if there's no other questions from 11.1, 11.2, we're actually going to get into 11.3.
Magnitude of u and so yeah.
I don't quite understand what we did before. So we multiplied u.
Yeah, so real quick, direction of u is this piece.
Okay.
So that's the direction. No, the length is 1, so it really is just a directional thing, right? For lack of a better word.
Okay.
This tells me the direction I'm pointing in, and I want to be this long.
Okay.
So that's why I like the idea of anytime you need a problem like that, I got a vector that tells me what direction I want to face, but I want to be able to build on that to be certain lengths, then I make this into a unit vector. Now I can build on that easily, right? So first thing we did was we made it into a unit vector, and then I built on it to make it as long as I wanted it to be. Cool. Okay, cool. So 11.3. Now we're getting into multiplication of vectors, which only makes sense. I mean, this is how we've done things from the beginning of algebra. You learn radicals, and then what do you do with the radicals? You add them, you subtract them, you multiply them, you divide all this stuff, right? So we're sort of following the same thing. We learn vectors, then we learn how to add them, how to subtract them. That has graphical meaning too, but that's still learning how to do those. Now we're going to learn how to multiply them, and there are two methods for multiplication. The first method is dot product, and there's a nice physical meaning behind this. So just go with me on this. This is a decent example, I think. So let's say, for example, there's this box, right? There's a box, and somebody wants it moved in this direction, and they're willing to pay. What did I say? Doesn't really matter. Yeah, $10 a foot. That is moved this way. You guys with me? That's pretty simple, right? So I'm like, yeah, sure. How heavy is this damn thing? Let me move it. I'll get some money. And what it turns out is there's like grooves in this. I'm thinking about this as like a parking lot. They want that moved over so cars can park here or whatever. And it would just be easier if I moved it this way. It's just physically easier if I move it that way. Like it's going to run along a groove. How are we doing so far? So he doesn't care. This person doesn't care where over here it ends up. He just wants it over there. You guys with me? Now, obviously, this is a problem that a math teacher came up to explain a mathematical concept. Because when the hell does this happen? Has anybody ever had this happen to them? No. Yeah, that's exactly what I expect. But just go with me. Physically, it makes sense. So obviously, if I move it so many feet along here, am I going to get paid that many feet times $10 a foot? No, because he's only going to pay me based on how far I move it that way. And you guys can see where this is going. Somehow, what's got to come into play? Trig, which means that the angle has to come into play. Right? So let's say I'm at an angle of, what did I say? 30 degrees, I said. Let me put my 30 degrees to this. I'm going to move it there. And let's say I move it 20 feet in that direction. Right? How much do I actually get paid?
20
And of course, that's this piece here, right? You're going to get paid that length times $10 a foot. Of course, that's very simple physically. That makes sense. How we doing so far? That, what I just drew there, is going to become very important later. I've already said the word once, the projection of something on something else. That's going to become important. Right now, it's just good old trig. I just made a little triangle there. So like you guys said, it'll be 20. The length I went is 20 cosine 30. And it's $10 per foot in that direction. And so whatever that, what's cosine at 30?
10 root 3. Root 3 over 2.
Root 3 over 2. Right, so it'll be 20 root 3 over 2, which is 10 root 3 times $10 is 100 root $3. Right, and I want exactly 100 root $3. Because I measured my damn angle. Give it to me. All right, is that how we doing there? I mean, that by itself was simple mathematics. You could do that outside of a 281 class. You could do that back in pre-calc, right? But here's what idea it illustrates. Obviously, it illustrates this. And what did we just do? We did the component of this that lies in this direction times the length in that direction, right? So the dot product, which thankfully we use a dot to represent it. That makes sense. So that's the dot product of two vectors. it is, and really, if I call this the u vector, what is this then? Careful, what's 20 cosine 30? U cosine 30, right? In fact, it's the length of u cosine 30. Is that cool? Well, cosine, let me make this more, sorry. Thank you. Cosine theta in general, right? So this is like our 20 cosine 30, for example. How we know so far? So this is just the amount of u that lies in the direction that I want to go in, times, and really here this is a implied length. It's $10 a foot, but it's got a direction to it, so it's the length of the vector v. You guys cool with that? Times the length of v. Because what's my pay vector really? This is my, let me see if you can answer it with me. That's my pay magnitude. Let me see if somebody can get this. What would be my pay vector? How many dimensions do I have here really? Just 2. Yeah, my pay vector, you could write it like this, 10, 0. I think somebody said that. Or what's another way to write it? 10, I, 11. Cool. You guys with me? So what did I really multiply then by? I multiplied by its magnitude. So you guys cool? The math we did here is this in general. How we doing? And you see how it makes sense that this is a multiplication. This is a more complicated multiplication than just 5 times 7 because now vectors involve direction. So that has to come into play here somehow. So the way we normally write this is u dot v equals length of v, cosine theta. Okay, cool. So when will the dot product be 0?
With a perpendicular.
Good. When u and v are perpendicular, which we won't hear the word perpendicular much in here. What we'll hear, no, orthogonal, which works as an exclamation also. That's orthogonal, or maybe not. Amongst math geeks, yes. How we know so far? Orthogonal. So that's a brand new term for some of us. That just means 90 degrees perpendicular. That's what that means. So you're orthogonal to something. Notice something about this formula. This formula sort of sucks. Why was this problem easy? Because one of the things I gave you that you didn't have to calculate was the angle. I gave you the angle. Can somebody tell me the angle between these two? Could I then use that formula to figure out the dot product of these two things?
Yep.
No, I couldn't. Right? It'd be very difficult. In fact, what we normally do is we use the dot product to find the angle, which means that there must be some other way to calculate this than one based on the angle. Right? And why should that make sense to us? Because the vectors themselves inherently have a direction. I shouldn't need to pull the angle out of it. There should be another way to do this, purely using what I see in the vectors. That's what I said earlier, right? Vectors have the angle in them. I shouldn't have to tease it out. Otherwise, why do freaking vectors? Okay, all right. So I need a little help from you guys. We got this here. This is not an offer, by the way. Don't find a box and start pulling. I'm not going to pay anything.
It's a lot of money to move off.
I know that.
It's gonna be heavy.
It's a heavy box. Heavy box.
One of those crates.
So let me make this in a certain way. Just keep it the same as my notes so I won't freak myself out. And just for the sake of later, when we start looking at this as vectors. Yep. Cool. But right now, that's just a triangle with sides ABC. And let's say I know this angle here. Or it's just part of just one of the variables involved. What's the relationship between the side lengths A, B, C. Who remembers what law I must use?
Law of cosine.
Law of cosines, cool. Law of sines is good when I know two sides and their corresponding angles, or I have two sides and an angle or something, right? I mean, right now I got three sides and one angle. I can't really. Yeah, law of cosine. So what does the law of cosine say?
Okay.
Sine A will be equal to C.
Considering I know that angle across from that side, C squared equals A squared plus B squared. That sounds very familiar.
Minus 2AB times cosine of
Theta. Or cosine, yeah. Cosine, normally we call this big C, but let me just call it theta. How we doing? We good? Theta obviously must be the angle between A and B that's correlated to side C. Does that sound vaguely familiar? Yeah. It must, yeah. So instead of A, B, and C, of course, I'm going to give these vector names. So let me name a couple of these, and you help me name the last two. And no, W is not acceptable. What would C be then?
D.
And actually, let me say this is the length, because these are really.
C would be B squared plus U squared.
A minus B.
One.
A minus B.
So it's going to be.
U minus B.
Yeah, wouldn't it be V minus U?
Why isn't it the tail of
Because how far apart are those two vectors when you say they're that far apart? So that must be their difference. Remember how they get the difference of two vectors? Is the vector that's directly between the endpoints, right? Okay. Yes?
Does it matter which one is subtracting the other?
Not really, because in this case it doesn't. If I got it wrong, then why does it matter in this case? Because these are all magnitudes, right? Mm-hmm. These are magnitudes. So I could, if I wanted to. I really could. I could say this is the same as that, right? So I kind of did that on purpose. I really wanted it to be U minus V. It wouldn't change anything, but I just want to keep it that way. So you can refer to the book. The book actually does what we're about to do. But I want to step us through it a little bit so you see where this comes from. Because this is huge. Everybody understands that this thing sucks. It really does. In general, it sucks because I can't find the angle. I'd love to be able to use this to get the angle. That would kick so much ass. If only there was another way to get this stupid thing. And there is. We're going to prove it right now. We're going to figure out what that other way is. So in place of here would go what?
squared.
Equals A squared plus B squared minus 2A B cosine theta. Now, let me let you guys write that down. This piece should look hopefully familiar. Yeah. So I can rewrite this as U minus V squared equals U squared plus V squared minus twice U dot V. That's that dot product, right? So obviously, do you guys see how this works now? If I figure out what this other shit is, it'll be another way to express U dot V. And is there any angle in here? No, so I'm not going to need the angle to do the dot product. There's a whole other way to do the dot product, thank God. And the dot product is silly important to be able to do it. So all we got to do now is figure out, can somebody give me an example? Let's just say we're working in 3 dimensions here, right? Let's set that up right now. We're going to work in 3 dimensions. It works in 2 also, but we're working in 3. So what's this? Be careful of that square. It's very simple.
U squared plus U2 squared plus U.
U1 squared plus U2 squared. So V would be the same thing with V's in there, right? Mm-hmm. And what's this? Beautiful. U1 minus V1 squared. Just to show you real quick, when you get u1, v1 in the first expression, if you FOIL this out, we can all FOIL. So let's kind of cut to the chase here a little bit. A lot of stuff's going to kind of cancel out here, possibly. So what ends up happening, well, not cancel out directly here, but you've got u minus v squared minus u squared minus v squared equals twice u dot v. How are we doing there? Yes, sir.
Oh, never mind. I'm sorry.
We doing okay? You guys, all I did was pull that over, trying to solve for the dot product.
Yeah, but you missed the negative.
How'd
I
you
missed
get
the negative.
How'd you get the
Oh,
third?
sorry.
How'd you get the third line, Professor?
Where are we at?
Yeah, the third line.
Here?
Yeah, third line.
Oh, here. These are just definitions.
Yeah.
And of course, how would you get the length of u minus v? What would you have to do first? What is vector u minus vector v? Wouldn't it be u1 minus v1,
Right.
comma u2 minus v2? So how do you find the length of that? u1 minus v1 squared plus u2 minus v2 squared. So what is u minus v? And that u1 minus v1. So what's the length of this? The first p squared plus the second p squared plus the third p squared, square rooted, but it's squared there, so that's where it goes away. How we doing? Hopefully more of you are more bored than anything. This isn't anything major, really, right? Foiling. So just to cut to the chase, let me do this. So between these and this, a lot of stuff cancels. So I'm just going to take it on faith that you all can do it. And what you end up with is 1/2 u1 v1 plus u2 v2, not 1/2. Twice, because all the little middle pieces here, isn't it 2 u1 v1?
Yes.
2 u2 v2, so forth. And of course the u1 squared, u2 squared, u3 squared cancels with those pieces. You guys with me? You can kind of see it happening. If you don't trust me, you can do it. And then trust me. So look at this beautiful damn thing that came out. This is almost what I could have started with, and just if I would have remembered, I would have done this. I'd say, what would you hope multiplication of vectors would be related to? Multiplying the components. Wouldn't that be awesome? Isn't that basically what this says? The one twist is it throws in, you multiply the components, but you add them together. Now we do. So now the dot product is u1 v1 plus u2 v2 plus u3 v3. What if I was in 4 dimensions? Plus u4 v4, and you can do the similar. The math would work the same way. 80 dimensions, you just keep on adding up to 80, right? Notice something kind of strange. Of course, you're probably all like, the whole damn thing is strange. But when I multiply 2 real numbers, what kind of answer do I get?
A real number.
When I multiply 2 matrices, this might be, I don't know if you guys have done that, but when you multiply 2 matrices, you get another matrix. It's the idea of closure. Have you guys ever heard of that property? The property of closure. For example, integers are closed over addition, because if you add 2 integers, do you ever get anything that isn't an integer? No. So it's closed. The answer is the same type of thing as what you started with. What do you get from a dot product? You get 2 vectors as inputs. What's the output? A number, a scalar, right? So on one level, this makes total sense as far as what multiplication for vectors would be. And that was going back to the idea of if you move it this way, I give you $10 a foot, and I move it that way. The multiplication should kind of physically make sense, right? But on another level, it's kind of dissatisfying because it's not closed. I start with 2 vectors and I multiply them, and it becomes a totally different species, right? Maybe you guys are with me. You guys with me on this? I mean, it shouldn't bother you that much. This is just a mathematical construct. But this is why there's a second method of multiplying vectors. It's not why, but it's a good reason for there to be. Because I want to do something to 2 vectors and have the answer still be a vector, so it's nice and closed. Right? We're kind of used to that. We're so not used to vectors that this probably wouldn't even bother you if I didn't say anything. You'd be still kind of absorbing what the hell this is. But let me show you the usefulness of dot product here. Now, real quick, if I give you two vectors in two dimensions, let's say this is to find the angle between these. Could somebody come up with a way to directly find that angle?
Take the angle of the bigger one minus the little one.
Okay, good.
First tangent.
So in two dimensions, this problem of finding the angle between two vectors is itself not difficult. I don't need to rely on any advanced mathematics. The minute I go to 3 or beyond, the problem becomes a lot more complicated, right? At 3, I can still do it. It's going to be multi-steps. Beyond that, it's going to be crazy difficult, nearly impossible. So let's just double check dot product usefulness for finding angles with something that we can find the angle of already. What's the angle for u? Let's call this one, incredibly enough, I'm going to call it theta u. So we'll call this one theta v. And this is actually something I don't think I've directly said in here. Somebody, I remember if it was on one of the quizzes or something. How do I find that angle? Inverse tangent. This is sort of like related to polar coordinates in a way, right? We got a r, we got a theta. So that's actually the same conversion. It'd be the inverse tangent of what?
3 over 2, 1 over 2.
Yeah, y over x. I love it.
56.
56.3. Thank you. And then the inverse tangent of 1/4. 14.03. Blah blah blah. So roughly, then theta would be
56.
yeah. So 42.27 roughly. How are we doing so far? Does that look all right?
Yeah.
So that's pretty simple. Let's check it with, let's try the dot product one. So here's something to realize. U dot V is this. That's the first definition we came up with. And then we went through some complicated mess just because this very often is difficult to figure out. So now we know that the dot product is also that. So can you use that to calculate the angle? Now in this case, in 2 dimensions, this is more work than necessary. But you guys have seen stuff like that. In fact, using matrices to solve something in 2 dimensions is more work than necessary. But using matrices in 5 dimensions, I don't know if you've ever done it, but it makes it, make a 1, make them zeros, make a 1, make them zeros, make them 1. You guys remember doing that? Have you ever done the Gaussian elimination, the row reduced form? If you haven't, then just go with me. There's a thing that's harder to do this in 2 dimensions, but the minute you get out of 2 dimensions, it's easier to do it this way. So we're just verifying. What is the length of u? Square root of 13. What's the length of v? Square root of 17. Be careful. Don't forget that roots. The only reason the other ones didn't have roots is because they were squared. On the problem we did before, right? Cosine theta, that's what we don't know. Equals. And in fact, I put too many things up here because we were talking about 3 dimensions, but we only have 2 dimensions here, right? So u1, v1, 8 plus u2, v2, 3. So theta is the inverse cosine of 11 divided by that thing, right? That's times. So put that in your calculator. Why? Shoot. My calculator is currently taking a video. Oh.
2.3.